Lesson 74, uniform motion with both distances given. All right, we have talked about uniform motion problems before. We worked problems where when we first started off, the distances traveled were equal. All right, so we had rate times time was equal to rate times time. We worked problems where the sum of the distances equaled a total. So we traveled a certain distance plus another certain distance, and that gave me a total. We also solved problems where distance B was greater than distance A by a certain amount. All right? These equations that we are working now, both distances are given. However, we're going to be looking for both rates and both times. Now, if we're looking for both rates and both times, that means that we have four things that we're solving for. All right? These equations actually can be set up using two variables, okay, two unknowns, which means we're going to end up with two equations, okay? But we're going to be solving them kind of like we did the abstract equations where we had multiple substitutions. All right, so we'll work two of these together, and then we'll have you work one out on your own. All right, let's remind ourselves, first of all, though, of a couple formulas for these problems. All right, we have rate times time equals distance. This is the basis. This is the foundation. This is the equation that we base every other problem off of. Okay, rate times time equals distance. All right, we talked about equal distance problems. So distance 1 was equal to distance 2, which meant that rate 1 time 1 was equal to rate 2 time 2. Okay, we did problems where distance 1 plus an k amount was equal to distance 2. All right. So we're going to use these different equations to solve these problems. All right, so go ahead and get out your example sheet. Let's take a look at some examples on here. All right, if we take a look at this first example, all right, it says, Friar Tuck rode the 24 miles to the fair in Nottingham at a leisurely pace. He stayed too long at the fair and had to double his speed on the way back in order to get home on time. If his total travel time was 9 hours, how fast did he travel in each direction, and what were the times? All right, we are asked a lot of information in this problem. We're also given a fair amount of information in this problem. All right, we know that Friar Tuck rode the 24 miles to the fair. Okay, so he went a distance of 24 miles. Okay, he went it at a leisurely pace. We don't know what his time is. We don't know what his rate was. Okay, but we do know that his distance 1 was 24 miles. All right, so we're going to go ahead and go distance 1 is equal to 24. All right, again, we don't know what the rate is yet, and we don't know what the time is yet. All right, we also know that on his way back, he had to have gone the same distance. Okay, if he was going from the fair back to wherever he started, it would be the same distance. So his distance 2 is going to be equal to 24 also. All right, again, we don't know the rate, and we don't know the time. Okay. All right, now let's look at our other information. It says that when he got to the fair, he stayed too long and he had to double his speed on the way back in order to get home on time. Okay, so whatever his rate was there, he had to double it on the way back. So if we called his rate there A, then his rate on the way back would have to be 2A because it was doubled. Okay? All right, now let's talk about his time. His total travel time was 9 hours. Okay, so we don't know how long it took him to get there. We don't know how long it took him to get back. But if we gave him a travel time of X on the way there, then however long it took him to get back would be 9 minus X. Okay, so now we have two equations with two unknowns, and we can go ahead and solve. All right, let's solve using the first little diagram over here. Remember, rate times time equals distance. Okay, so this equation is going to be A times X equals 24. All right, on this side, we're going to have 2A times 9 minus X is also equal to 24. Okay, now from those two equations, we can go ahead and solve. Now this looks like those advanced substitution problems, which it is. All right, so we are going to go ahead and solve. I'm going to use this second equation here to solve for A. Okay, what I'm going to do is we're going to start off by distributing. All right, so 2A times 9 is 18A. And 2a times negative x is minus 2ax, and that is equal to 24. Now keep in mind, we know what ax is equal to. Ax is equal to 24. Alright, so we're going to go 18a minus 2 times 24 equals 24. Alright, 2 times 24 is 48, so we have minus 48 equals 24. Add 48 to both sides, we have 18a equals 72, which means that a is going to be equal to 4. Alright, so we know his rate on the way there was 4, which means his rate on the way back had to be 8. Okay? Alright, and then we can use that information to solve for x. Alright, so going back to our equation, ax equals 24. If a is 4, then that means x has to be 6, which means he traveled 6 hours on the way there, and he would have traveled 3 hours on the way back. Alright, we can check this. Okay, remember rate times time equals distance. So in the first diagram, 4 times 6 is equal to 24. And in the second diagram, 8 times 3 is equal to 24, so it checks out. Alright? Okay, let's go ahead and look at example number 2. Alright, I did not make this name up. It was given to me. Alright, so in the second example, Atalanta, it's not a typo, it's supposed to be Atalanta. Atalanta ran 4 times as fast as her challenger. In fact, she ran 80 miles in 2 hours less than it took her challenger to run 28 miles. How fast did each run and how long did they run? Okay, we know that Atlanta ran 80 miles and we know that her challenger ran 28 miles. Okay, so we're given a distance. So let's go ahead and start off by diagramming this distance. All right, we have Atlanta and her distance was 80 miles. And we have her challenger. Her challenger's distance was 28 miles. All right, Atlanta ran 4 times as fast as her challenger. So when we're talking about rate, if her challenger ran at rate x, Atlanta would have run 4 times x because she ran 4 times as fast. All right, now let's talk about our time. Atlanta ran in 2 hours less than it took her challenger. Okay, so if her challenger ran a y amount of time, Atlanta would have run y minus 2 because she ran 2 hours less. All right, now we have our 2 diagrams complete. Let's go ahead and make our equations using rate times time equals distance. So in our first one, the rate is 4x, the time is y minus 2, and it's going to be equal to 80. All right, in our second, our rate is x, our time is y, and it's equal to 28. From there, we can go ahead and use advanced substitution to solve our problem. All right, we're going to distribute in this first equation. 4x times y gives me 4xy. 4x times negative 2 gives me negative 8x, and it's equal to 80. All right, we know that xy is equal to 28. So in this equation, we can substitute 28 in for xy. All right, 4 times 28 is going to give me 112 minus 8x equals 80. If I subtract 112 from both sides, I'm going to have negative 8x equals negative 32, which means that x is going to be equal to 4. All right, so from there, we have found that the rate of the challenger was 4. Now, if her challenger ran at a rate of 4, then her rate would be 16 because it was 4 times as fast. All right, then we're going to go back to the equation xy equals 28, and we're going to substitute that 4 in, which means that y is going to be equal to 7. All right, so her challenger ran 7 hours, which means that Atalanta would have run for 5 hours because it was 2 hours less. Again, we can check this using rate times time equals distance. All right, we have 16 times 5, which is equal to 80. And we have 4 times 7, which is equal to 28. So everything checks out. All right, go ahead and work on example 3 in your example sheet. Finish this to completion, and we will check it when we come back to class.